right, we're going to do the notes for 6.3, some properties of some trig functions, although it's not until 6.4 that we're actually going to start to graph. So we are going to go through and fill in the blanks in these two explorations that will help us as we go through and we do the examples. So we've already talked about this. The sine of theta is the y. So if you have a point on the unit circle, that point being x, y, the y coordinate represents the sine of your theta, the x represents the cosine of your theta. And then from the sine and the cosine, we can come up with all of the other trig functions to give us our total of 6. So let's go ahead and let's read through this exploration and fill in some of the blanks. So use the definitions above to make conclusions about the domain and the range of the following functions. I'm going to, of course, help you out with that. To begin, make sure you're clear on what variable is the domain, which is, of course, the input, what goes in, and what variables or variable are the range, which is the output. So if we go in here, so for the sine of theta, they help us out here. The input is theta, so your angle, and the output is y, because we just talked about the fact that for our sine, the y coordinate is the sine of your theta, whatever your angle is. This means that the domain of the sine function is all real numbers, in other words, all of your thetas, any angle, and the range will be from -1 to +1. If you play with the sine function in your calculator, whether in radians or degrees, you will see that for sine, and cosine for that matter actually, you will never get a value that's less than -1 or greater than +1. Okay, for cosine, it's going to be the same thing. Your input is your theta, although remember for cosine, your output is your x. This means that the domain of the cosine function is, again, all real numbers. And the range is, once again, all values from -1 to +1. And notice that's inclusive because, for example, the cosine of 0 is +1. The cosine of pi, or 180 degrees, is -1. Okay, now tangent gets a little trickier. So for the tangent function, the input is, again, any angle that does not produce a division by 0, and the output is y over x. This means that the domain of the tangent function is all real numbers except for odd integer multiples of pi over 2. Because the tangent of pi over 2 is undefined. The tangent of 0 is 0. We're fine. But the tangent of pi over 2 is undefined, as is the tangent of 3 pi over 2. So when they say odd integer multiples of pi over 2, they mean 1 pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, and so on. It's only the odds that have a tangent that is undefined. For the cotangent, the input is, again, theta, and the output is x over y as opposed to y over x. This means that the domain of the cotangent function is, so again, you need all thetas, where the y, or the sine, isn't 0, because you can't have 0 in the denominator. So that would be all, so the domain is all reals, except for, and now when would this denominator be 0? Well, that would be when the sine is 0. The sine is 0 at 0. It's at pi. It's at 2 pi, and so on. So that would be all reals except for multiples of pi. So what we mean by that is 0 pi, 1 pi, 2 pi, 3 pi, 4 pi, 5 pi. And the range is going to be all real numbers for that. Now, when we actually go ahead and graph, you'll be able to see this visually, which will be very nice. All right, let's go for cosecant. So now let's remember, cosecant is 1 over the sine. So for cosecant theta, the input is any theta that doesn't produce division by 0 when the output is 1 over y. So it's again going to be everywhere where y, or the sine, is equal to 0. Those are the exceptions. So this means that the domain of the cosecant function is all real numbers except integer multiples of pi, or 180, which you know would be 0 pi, 1 pi, 2 pi, 3 pi, 4 pi, and so on. And the range is all real numbers. Now this is different. Greater than or equal to 1, less than or equal to -1. So again, the domain is all reals except for 0 pi, 1 pi, 2 pi, 3 pi, and so on. And the range is all reals x greater than, well, we should probably use y, I guess. Y greater than 1 or y less than -1. And finally, for the secant, again, the input is theta. The output is 1 over x. This means that the domain of the secant function is, now again, it's going to be very similar to what we did above, but it's all reals except for, and this one would be the odd multiples of pi over 2. So 1 pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, and so on. Because those are the places where the x would be 0, where the cosine is 0. These are the values of on the unit circle where the cosine is 0. And the range would be, again, all reals except for, so let's do not equal to, let's do it this way. I'm going to do it kind of consistent with what I did above. I'm sorry. All reals where y is greater than 1 or y is less than -1. Let's keep things consistent for you. And again, we're going to talk about domain and range a lot more when we actually look at the graph. So don't panic if some of this is going a little bit fast. You're going to be okay. So now, when we talk about trig functions, we talk about functions there that are periodic. And basically what that means is they repeat after a certain amount of time. So for example, if we look at, I don't know, I'm just going to kind of draw a graph here, a sine function. The sine function, and we're going to graph it, kind of looks like this. Well, you can see if it starts here, it goes to here, and then it begins to repeat. So that is what we consider one period of the sine function. It's one, I don't know what we want to call it, one pass at it before it begins to repeat. Okay, so that's what periodic means. So earlier we saw that the cosine of 420 is the same thing as the cosine of 60. How did we get from 420 to 60? Remember what we did is we just subtracted 360 because that is one full circle around. So when you subtract 360 or when you add 360, you get virtually the same angle. Sorry, I'm just trying to adjust here. Okay. So, based off our explanation above, in general, here's what is true. The sine of an angle plus 2 pi times k. So, let's talk about what that means. If I have an angle, and if I have 2 pi, for example, times 0, that would just be that angle theta. if I have 2 pi times 1. So k is just an integer. If I have 2 pi times 1, then that's 2 pi. Well, 2 pi, remember, is 1 full revolution. So if I take an angle and then I go from that angle 1 full revolution, don't I end up with an angle exactly the same place? Or if I take k equal to 4 pi. So every time I raise k, it just means that I'm making one more complete revolution, which means I'm ending up at the exact same place. So the sine of theta plus 2 pi k, which is the same thing as the sine of theta plus 360k, because of course 360 and 2 pi mean the exact same thing, is equal to the sine of theta. So there should be able to be a space there. So all of these are the same. Same thing with cosine. The cosine of theta plus 2 pi k is equal to the cosine of theta plus 360k, which is equal to simply cosine theta. So no matter how many times you add or subtract, by the way, 360, you're going to end up with an angle that looks exactly the same. Back when I taught high school, we called them coterminal angles. They were angles that looked exactly the same, like 420 and 60 look exactly the same. Okay, functions that exhibit this kind of behavior, where you can add or subtract something being 360 or multiples of 360 to an angle measure and the values of the sine or the cosine remain unchanged, are called periodic functions, and in general are defined as below. So here we go. So a function f is periodic if there's a positive number p such that whenever your angle theta is in the domain of f, so is that angle plus p. And if I find the y, f of theta plus p is exactly the same as f of theta. If there's a smallest such number p, then this smallest value is called the period. Okay, so again, we're going to talk a lot about periods, so don't panic if that's a little fuzzy. It's okay. So now, here are things that you need to know. The period of the sine function. So remember, I kind of graphed the sine function up here, and I told you that this is one full period right here because that's how far it goes before it begins to repeat. The distance on the x-axis, the domain from here to here, is 2 pi. So the period of the sine function is 2 pi. So it goes 2 pi until it begins to repeat. Cosine has the same period. It is also 2 pi. The tangent only goes pi units before it begins to repeat. So the period of the tangent function is pi. Now, how about our reciprocal functions here? Cosecant function is still 2 pi. It's the reciprocal of the sine function. The period does not change. Same thing with secant. It's the reciprocal of cosine, is still 2 pi. And guess what? The period of cotangent, still pi. So those are the periods of those. Okay, so how are we going to use it in this situation? Well, here's all you're going to do. I'm just going to kind of grab my calculator here. So find the exact values using periodic properties. All that tells you is, okay, 390, that's bigger than 360. So let's subtract 360, and we get the sine of 30 degrees. So the sine of 390 is exactly the same as the sine of 30. And if you think of your unit circle, and hopefully you've been practicing that, the sine of 30 is 1/2. That's all they're asking us to do. If I want the tangent, now we were looking at degrees there, so that's why I subtracted 360. If I look at the tangent of 19 pi over 4, notice here I'm talking about pi radians. So I can subtract 2 pi, which is the same thing as 360, actually, I can subtract 4 pi from here, and that's going to get me where I want to go. So actually, what I've done is I've subtracted 2 full revolutions. So that would be the tangent of 19 pi fourths. I'm getting a common denominator, minus 16 pi fourths. So that would be the tangent of 3 pi over 4. Okay, now think of where 3 pi over 4 is. It's out here. It's a 45, 45, 90 to here. Tangent is sine over cosine, which is going to be 1 because it's root 2 over 2 over root 2 over 2, but tangent's negative in this quadrant, so you should be getting negative 1 for your answer there. Okay, I think I'm going to stop this video and I'm going to do a part 2. So here we go.